Hello, and welcome to This Explainer. I am incredibly excited to take you on a journey today. A journey through one of the absolute most vital, yet honestly often overlooked processes in human survival. We're going to trace the path of a single breath, and not just through the human body, but through the completely ingenious mechanical guardians that take over when our own biology fails us. From oxygen concentrators to ventilators, all the way to complex anesthesia machines, we'll explore how medical engineering beautifully mirrors and, well, sometimes totally overrides our natural systems. Right off the bat, let's start with a quote that I think perfectly sets the stage for what we're talking about today. Inside a modern hospital, there is one invisible traveler, breath. Not just air, but oxygen, pressure, flow, gas exchange, consciousness, and life itself. You know, it is so incredibly easy to take breathing for granted, right? But when you really break it down, breath isn't just wind moving in and out of your chest. It's this intensely complex exchange of gases governed by the strict laws of physics. And when illness or surgery completely disrupts this natural rhythm, we have to rely on some pretty amazing technology to keep that invisible traveler moving.
Section 1. The Human Breathing Machine.
Okay, before we can really appreciate the machines we build, we absolutely have to understand the original biological machine. Our bodies essentially set the baseline rules for airflow, pressure, and gas exchange that every single piece of medical technology out there has to follow. And a huge part of this is something called compliance. Think about normal breathing. Your diaphragm drops, and that creates a negative pressure that actually pulls air inward. Your lungs act like these highly elastic balloons. So high compliance means they inflate super easily. Low compliance, that means they're stiff. And suddenly, taking a single breath becomes incredibly hard work. Add in something like airway resistance, say the tiny narrowing of the airways you might see in asthma, and your body is suddenly working overtime just to balance getting oxygen in and carbon dioxide out. It's a really delicate, continuous mathematical balancing act. So, here's the big question. What happens when this perfectly balanced natural system begins to falter? What happens when the lungs are still moving, the physical mechanics are working fine, but maybe due to something like pneumonia or COPD, the actual oxygen making it into the bloodstream drops dangerously low? At this point, the patient doesn't necessarily need a machine to literally breathe for them yet. They really just need more oxygen. Section 2. Harvesting pure oxygen. When the biological machine is starving for oxygen, that's when we bring in the oxygen concentrator. And the fundamental problem we're trying to solve here is actually surprisingly simple. Atmospheric air is mostly not oxygen. Yeah, room air is roughly 78% nitrogen and only about 21% oxygen. So, to help a struggling patient, we can't just blow more regular room air at them. That's not going to cut it. We actually need to actively harvest the oxygen out of the air. At its absolute core, an oxygen concentrator is just this intricate, amazing air separator. And the mechanical pathway inside one of these things is fascinating, because in a way, the machine actually breathes too. The whole process kicks off with a compressor pulling room air inside. You can basically think of this compressor as the machine's combined heart and lungs. It squeezes the air to a super high pressure, forces it through filters to strip away dust and any bacteria, and preps it for the absolute most critical step of the whole journey. Now we get to the actual soul of the concentrator. It uses a process called pressure swing absorption. Inside the machine, there are these columns filled with a specific material called zeolite, which acts literally like a microscopic molecular trap. Here's how it works. In cycle A, the machine pressurizes the first tank, and the zeolite physically traps all the nitrogen molecules, letting only the pure oxygen flow right past and out to the patient. Then, in cycle B, while the second tank takes over the oxygen delivery, that first tank depressurizes and basically exhales the trapped nitrogen safely back into the room. It just swings back and forth like this, doing this molecular sorting hundreds of times a minute. It is wild. And the result of this mechanical breathing rhythm is incredibly impressive. Standard and portable concentrators can take that basic 21% room air oxygen and boost it to an intensely pure 85 to 95% output. Plus, the machine is continuously monitoring its own pressure and temperature just to guarantee that this life-sustaining purity never, ever drops. But let's take this explainer to the next level. What happens when extra oxygen alone just isn't enough? What if the patient loses consciousness or their respiratory muscles completely fail and the lungs become physically too weak to move air at all? Well, now the problem isn't just about oxygen concentration anymore. It's about taking over the physical movement of the air itself. Section 3. Mechanical breathers and pressure. When a patient simply cannot ventilate on their own, the mechanical ventilator enters the story. And here is where it gets really interesting, because an artificial breathing system actually requires a complete reversal of human physiology. Remember how we just talked about human lungs using negative pressure to naturally suck air inward? Well, a ventilator does the exact opposite. It uses positive pressure ventilator. It literally forces gas down into the lungs under pressure. It's a highly effective but honestly deeply unnatural process, which means it requires absolute precision so we don't accidentally damage that incredibly fragile lung tissue. Think about the basic layout of a ventilator circuit. The machine pushes a really precise mixture of warmed, perfectly humidified air and pure oxygen down into the patient's airway, and then it passively lets the exhaled air flow back out. But the real magic, the thing that makes this safe at all, is the continuous monitoring. A modern ventilator is basically a high-powered, real-time computer. It is constantly measuring pressure, volume, and flow. It literally translates the physical stiffness of a patient's lungs into digital waveforms on a screen that clinicians can read instantly. Now, to safely deliver all this air, ventilators generally operate using one of two distinct philosophies. First, there's volume control. Here, the machine guarantees an exact specific volume of air gets pushed in with every single breath, but the pressure will fluctuate depending on how stiff those lungs actually are. The risk, of course, is that high pressure can cause injury. On the flip side, we have pressure control. In this mode, the machine guarantees a maximum safe pressure limit, but the actual volume of air delivered might vary from breath to breath. And this approach is generally much safer for extremely fragile lungs, like what you'd see in premature babies or patients with really severe lung disease. Oh, and there's one more critical tool the ventilator uses. It's called PEEP, or positive end expiratory pressure. You see, when you breathe out normally, the tiny little air sacs deep in your lungs, the alveoli, can sometimes completely collapse. By maintaining a baseline of positive pressure even at the very end of an exhalation, the ventilator essentially props those tiny air sacs open. This brilliantly improves oxygenation. But again, it's a total tightrope walk. Too much PEEP, you can actually squeeze the heart and dangerously drop the patient's blood pressure. Absolutely everything is a careful balance. Okay, so we've covered supporting natural breathing, and we've covered replacing it. But what about when we actively need to turn breathing off entirely? How do medical teams safely stop a patient from breathing consciously, but keep them completely alive and totally pain-free during a major surgery?
Section 4. The Master of Consciousness.
The operating room is a whole different beast, and it requires something absolutely extraordinary. It requires the merging of gas delivery, ventilation, and some incredibly deep pharmacology. The anesthesia machine is essentially the ultimate fusion of everything we've talked about so far. It is literally a master controller of both breathing and consciousness. The machine takes highly pressurized oxygen, nitrous oxide, and medical air, runs them through these incredibly precise flow meters, and then passes them through vaporizers. And those vaporizers do something that almost looks like magic. They carefully convert liquid anesthetic drugs into a perfectly breathable gas at perfectly precise concentrations. To actually control how deep asleep a patient is, anesthesiologists rely on a specific metric called MAC, or minimum alveolar concentration. Simply put, this is the exact concentration of that vaporized anesthetic needed to prevent movement in 50% of patients. And it's a bit counterintuitive, but a lower MAC number actually means the drug is highly potent. The machine lets the anesthesiologist seamlessly dial this concentration up or down, constantly playing this balancing game between the depth of the anesthesia, the patient's blood pressure, and their oxygen levels. And honestly, one of the smartest engineering features of the entire anesthesia machine is something called the Circle breathing system, to save these super expensive anesthetic gases and also to keep the patient's airway nice and warm. The exhaled breath isn't just vented away into the room. Instead, it gets pushed through a canister filled with a chemical called soda lime. The soda lime actively scrubs the toxic carbon dioxide right out of the exhaled breath. This brilliant little loop allows the pure oxygen and the expensive anesthetic vapor to be safely rebreathed by the patient, just going round and round in a circle. Section 5. Safety and redundancy. Look, at the end of the day, we are dealing with literal life and death at every single second with these machines. So the absolute crucial philosophy binding the concentrator, the ventilator, and the anesthesia machine together is this: they never, ever trust a single pathway. Redundancy saves lives. These machines are literally packed with overlapping failsafes. If the oxygen supply suddenly fails, a loud alarm screams immediately. If the airway pressure spikes too high, a physical relief valve pops open to protect the lungs. If the patient stops breathing unexpectedly, an apnea failsafe automatically triggers mechanical backup breaths. And if the entire hospital loses power, built-in backup batteries instantly take over. Preserving the safe delivery of oxygen is, without question, the ultimate prime directive here.
As we wrap up this explainer, let's take a moment to reflect on this really profound summary from our source material. It says, they are not merely hospital devices. They are engineered conversations with the lungs themselves. I love that. From the oxygen concentrator harvesting literal life from thin air, to the ventilator acting as an artificial muscle, all the way to the anesthesia machine mastering human consciousness, these aren't just tools. They are evolutionary layers of respiratory support. They act as true technological extensions of our own bodies. Which leaves us with a really fascinating thought to take away today. We've mastered positive pressure, we've mastered molecular air separation, and we can vaporize anesthetics flawlessly. But as artificial intelligence and real-time biometric sensors continue to rapidly evolve, how might the next generation of machines learn to speak even more seamlessly with our lungs? Will they be able to anticipate a collapsing alveolus before it even happens? It is such an amazing frontier. Thank you so much for joining me on this journey today. Keep learning, keep questioning, and I will catch you in the next explainer.